My name is Oleksandr Tovstolytkin, and I'd like to present to give the talk Magnetic Nanocomposites for Advanced Technical and Medical Applications. The work was done in collaboration by scientists from 3 institutes: Institute of Magnetism, Kyiv, Ukraine, Royal Institute of Technology, Stockholm, Sweden, and Vernadsky Institute of General and Inorganic Chemistry, Kyiv, Ukraine. How can I switch? It doesn't work. Okay, this is outline of my talk. After motivation, I'll concentrate on features and prospects of antiferromagnet-based nanomaterials. Then I turn to composite nanoparticles for magnetic hyperthermia. And finally, I will conclude. Okay, magnetic materials have found a number of applications in various high technology branches. Here you can see that that these materials are used in information technologies, in communication systems, in medicine. Advantages of these materials: wide range of functionality, high speed, wide limits of the parameters reconfiguration, and stability and reliability of work. Current trends of development these materials: further reduction in size, increase in speed, and enhanced performance. So the motivation of this work is increase in speed, expansion of functionality. And in my talk, I'll concentrate on antiferromagnetic nanostructures and multifunctional composite nanomaterials, mainly for medical applications. Let us consider the features of radiation in the terahertz band. Specific features of this radiation: reduction of the wavelengths implies the prospects of the transition to sub-micrometer element sizes. The ability to penetrate through thin layers of paper and skin. Dependence of the response on the type of living tissue. This means ability to identify certain types of viruses, distinguish disease-affected cells from healthy ones. At the same time, there are a number of problems that hindered development of new devices. Problems: generation and modulation of coherent electromagnetic signals in this frequency range requires the development of new devices and technologies. We suggest antiferromagnets as promising materials for applications in the terahertz band. Specific features of these materials: antiferromagnetic resonance frequencies are in the terahertz range. Antiferromagnetic ordering is observed in both metals and dielectrics. At the same time, a number of problems. Zero or negligibly small resulting magnetic moment means that there are difficulties in measuring magnetic parameters. Limited data on the transformation of magnetic parameters when moving to submicron sizes. Lack of information about processes at the antiferromagnetic-ferromagnetic interface, and limited data on the ways to control antiferromagnetic parameters. To solve this problem, we studied 3 kinds of samples. Here are objects of investigation. First set of samples are 3-layered nanostructures where antiferromagnet mediates interaction between 2 outer ferromagnetic layers. In this set of samples, we can obtain indirect information about thickness-dependent transformation of antiferromagnet parameters. Next, set of SEMs are antiferromagnet, ferromagnet bilayers. Here we can study the processes near antiferromagnet, ferromagnetic interface. And the third set of SEMs is synthetic antiferromagnets, where two ferromagnetic layers are divided by a non-magnetic one. What concerns the first set of SEMs, I mean two ferromagnetic SEMs, which are separated with antiferromagnetic spacer. With the decrease in thickness of antiferromagnetic spacer, we expect that we observe different kinds of behavior. For the case for very thin, very thick antiferromagnet, here you can see in the upper figure, we can obtain hysteresis loop, which consists of two partial hysteresis loops. If we expect that if the thickness of antiferromagnetic spacer is decreased, then we expect very wide hysteresis loop. And then for the case where antiferromagnetic spacer is very, very thin, we can expect that ferromagnet will polarize antiferromagnet, and there will be a thin hysteresis loop, but with relatively small coercivity. Well, we fabricated and studied these sets of three layers consisting of permalloy and iron divided by antiferromagnet iron manganese. And you can see the thickness of antiferromagnet spacer was varied from 4 to 18 nanometers. And here you can see in the center, you can see the dependence of coercivity on the thickness of antiferromagnetic layer. And we see that with the decrease in thickness of the antiferromagnetic layer, we observe the same, almost the same pictures as we expected. So for the very thick antiferromagnets, we observe the hysteresis loop, which consists of two parts. For at about 6 nanometers, we observe one hysteresis loop, but with very high coercivity, and at 4 nanometers, we observe a single hysteresis loop with reduced coercivity. We also studied ferromagnetic resonance, and we were able to distinguish, to obtain signals with one ferromagnetic layer and second ferromagnetic layer. And our idea was to study magnetic, quasi-static magnetic properties, to study resonance properties, and thus to obtain information about the parameters of antiferromagnetic spacer as its thickness is decreased. So we studied temperature-dependent magneto-optical Kerr effect. We studied magnetic resonance, and here are key findings of our investigations. The ferromagnetic layers are individually and independently exchange biased for thick iron magnetic spacer, more than 10 nanometers. The second regime, the coupling between two ferromagnetic layers divided by antiferromagnetic one appears on decreasing the iron manganese thickness below 9 nanometers. In this second regime, the interlayer coupling exists only in a finite temperature interval just below the effective Néel temperature of the spacer. The third regime, with iron manganese thinner than 4 nanometers, is characterized by a much stronger interlayer coupling in the entire temperature interval, which is attributed to a magnetic proximity-induced ferromagnetic exchange. Next kind of SAMs were two-layered SAMs, where ferromagnetic permalloy layer was in contact with antiferromagnetic, and the thickness of antiferromagnet layer was changed. The interesting results of our investigation you can see on the right figure, where magnetization of this bilayer as a function of thickness of antiferromagnetic layer is shown, and we see that at about 3 nanometers, the thickness of antiferromagnetic layer, we observe increase of magnetization. The other interesting thing is these bilayers is that we observe for the sample with 3 nanometers thick of antiferromagnet, the increase in frequency of ferromagnetic resonance. So key findings from these results are isotropic almost tenfold FMR frequency enhancement in these permalloy iron manganese bilayers, resulting from a complex interplay between ferromagnetic and antiferromagnetic type interfacial effects. Next set of SAMs is temperature-controlled synthetic antiferromagnets. Everyone knows that a typical synthetic antiferromagnet consists of 2 ferromagnetic layers divided by non-magnetic spacer. What we did, we used instead of non-magnetic spacer, a spacer with diluted ferromagnet. So it undergoes, this spacer undergoes a transition from ferromagnetic to paramagnetic at some temperature, and thus we obtain the temperature-controlled synthetic antiferromagnets. We studied a number of samples with different thickness of spacer, with different composition of spacer, and we really observed by magnetometry measurements and by resonance measurements this transition for all this structure. So advantages. Additional factor, namely temperature, is introduced to control the properties. This results in expansion of functionality. Also challenges, a need for further optimization of the parameters. Next step is related to the multifunctional composite nanomaterials, mainly for medical applications. The advantages of magnetic nanoparticles with the aim of their use in medicine are the following: the possibility to deliver nanoparticle-based entities to a target area, and the ability of nanoparticles to hit themselves and surrounding tissue under the action of AC magnetic field. We concentrate on the latter property, and we tried to develop magneto-nanoparticles with the aim to use in magnetic hypothermia. Magnetic hypothermia is based on intratumoral or intravenous injection of magnetic nanoparticles into a tumor and subsequent exposure of the tumor to an alternating magnetic field. Advantages of this approach: selective delivery to the target volume, the ability to treat deeply located tumors, the ability to be applied in combination with radiation and chemotherapy, and minor side effects. Actually, now there are a number of approaches to fabricate sophisticated nanoparticles with very interesting properties. We, in our investigation, we concentrated on core shell structures. Two sets of core shell nanoparticles with a fixed diameter of core and thickness of shells up to 2.5 nanometers were synthesized. We have shown that these nanoparticles are actually consisting of core and a layer with controllable thickness of outer layer. We studied magnetic and resonance properties of these structures. We applied some model to approximate the magnetic behavior, temperature dependence of magnetization of these structures, and thus we succeeded in finding effective anisotropy constant and magnetization. We found the regularities of the change of these parameters as a function of thickness of outer layer. And also we found nanoparticles whose parameters are optimized for the use in magnetic anisotropy. And here on the right picture, you can see the results of study heating of magnetic nanoparticles in AC magnetic field, 300 kilohertz, 100 Ørsted. And we can see that nanoparticles with a thickness of outer layer, 1 nanometers, are well suited for this aim for the use in magnetic hyperthermia. So key findings: creation of composite core shell structures is a viable way to tune the properties of nanomaterials for magnetic hyperthermia applications, and also a number of challenges, unfortunately. Need for further optimization of the parameters, necessity to increase heating efficiency, biocompatibility, stability in biological environments. As a result of all our work, I can summarize. The directions to expand the functionalities of magnetic nanostructures have been suggested and partly implemented. The ways to probe the parameters of antiferromagnetic components in composite nanostructures have been outlined, and the ideas to develop novel applications have been suggested. Thank you for your attention.